Hello, everyone. For those who are interested in my content on black holes, I have already recorded a video talking about more complicated black hole structures, namely black holes with charge, and how we yield charged black hole solutions by solving the Einstein-Maxwell equations and how we derive the Reissner-Nordstrom metric. However, I also plan on diversifying my channel and talking about physics outside of black holes. Firstly, I will continue my lecture on cosmology. Then I will start 3 new lecture series, the first of which is on nonlinear dynamics and chaos theory. Then I will talk about mathematical structures of quantum mechanics. And now I will talk about classical and quantum optics. And since this video is on classical and quantum optics, I will first talk about electromagnetic waves in free space. So let's start. The outline of this lecture is as follows. First, I will show how the Maxwell equations can yield wave solutions. Then I will talk about how normal modes yields electromagnetic plane waves, and how these plane waves are solutions to the Maxwell equations. Then I will represent the plane waves in a more beautiful form, namely the complex representation. And then afterwards, I will talk about how we can use complex representations to superpose plane waves. Next, I will talk about how the phase change in electric fields can yield different shapes of electromagnetic waves, and this phenomenon is called polarization. And afterwards, I will talk about polarization in a more enlightening manner by showing how we can yield different polarizations using the Jones vectors. So let us recap on what the Maxwell's equations are. So these are the Maxwell equations in Gaussian units. So to convert from SI units to Gaussian units, we simply replace epsilon naught with 1 over 4 pi and mu naught with 4 pi. So let us talk about each Maxwell equation first. The first Maxwell equation is Gauss's law. And notice that all these equations are in differential form. And the reason why I wrote this in differential form is because it allows us to more easily solve differential equations. But I guess integral form is more geometrically enlightening. So if we take the volume integral of both sides, we can then utilize divergence theorem to show that the enclosed charge and the volume of the enclosed charge tells us information about the electric field. Similarly, we have another equation that is similar to the Gauss law. It is so similar, it's called Gauss's law of magnetism. But notice that the right-hand side is 0. What does this mean physically? This means that we negate the possibility of magnetic monopoles. But there are higher theories that suggest that magnetic monopoles do exist. So what do? We basically do the same thing with electric fields and add a magnetic charge on this side and say, oh, basically we have the divergence of the magnetic field is equal to 4 pi over c times the magnetic charge, which we usually denote by rho sub m. Then we have Faraday's equation. And what does this represent? So we notice that this side is a curl instead of a divergence. So what can we do? We can take the surface integral of both sides and utilize Stokes' theorem. So taking the surface integral of the right-hand side, we yield the time derivative of the magnetic flux. And on the right-hand side, we have the surface integral of the curl of the electric field over some surface. But what we can do is use Stokes' theorem, and we get the line integral of the electric field. So we can deduce that the line integral of the electric field is influenced by a changing magnetic flux. So this is how we generate power normally. We have a magnetic field, and we have a moving wire or something like that. And basically this generates an electric field, which we can convert into voltage. So which is quite nice. Similarly, we have another equation, which is the curl of the magnetic field. And this is similar to this equation, but there's an additional term here, which is due to current density and surface currents. So these 4 equations are quite similar. And what you will notice that these 2 equations are coupled. So what is nice is that we can uncouple them using differential operators. But I guess there are caveats to this equation. First, the curl and divergence are only defined in 3 dimensions. And secondly, these are four equations, which is quite, well, it's not hard to deal with, but it's, I'll show you eventually that if we use another method, we can condense these four equations into two equations. So normally I would like to do, if we have a set of differential equations, I would like to represent them as differential forms, so using one forms or two forms. But I am aware that not many physicists, well, not maybe not physicists, but not many people are generally aware with the concept of differential forms. So what I will do is use a more convenient form, which is the tensor form, which is equally as powerful because they can be generalized to an arbitrary number of dimensions. So both of these forms are quite nice. So we can write the four Maxwell equations into two equations, namely this one and this one. So the first equation is that we take the partial derivative of the Faraday tensor. So what is the Faraday tensor? The Faraday tensor is basically the anti-symmetrized derivative of the four potential. And the four potential is just a vector where the time component is the scalar potential and the spatial components are the vector potential. Similarly, the four current is defined in a similar manner, where the four current is a 4D vector, and the time component is represented by the represented by the charge density, and the spatial components are represented by the current densities. So we can see that since this equation has J beta, it basically condenses this one equation. Represents equation 1.4 and 1.1. So these two equations are condensed into one equation. Similarly, one can utilize the Bianchi identity. So basically symmetrize. So basically, if we change all of these to different indices and then we symmetrize them, basically we get this. And this is as a consequence of basically what we have to do is we have to take the covariant derivative and we have to show, and since the covariant derivative of the metric is 0, we get this expression. So by using this equation, we can see that this represents equation 1.3 and 1.2. So these four Maxwell equations are condensed into these two equations in tensor form, which is quite nice. Now, before I talk about how we get the Faraday tensor, let us talk about how differential operators are represented in tensor form. So for example, here, if we have partial sub I with a scalar function, this represents, so basically this will yield a vector, right? Because this has an I index and this has no index. So this will eventually yield something with an I index. So basically this will become a vector. So this partial sub I with a scalar function will always yield a gradient function. But if this phi term has an I index in the upper indice, this will represent a scalar, right? Because I index in the lower index, I in the upper index cancels out. This will yield a scalar. So what does this mean? So remember that the divergence of a vector is always a scalar. So a partial derivative in the lower index and a vector with an upper index yields the divergence. And I will talk about the curl a little bit later because it involves something called the Lissajous symbol. But the electric field is defined in this manner, where we have the negative gradient of the scalar potential and the negative time derivative of the vector potential. And so basically here, the magnetic field can be represented as follows. And what does this the vis-a-vis symbol mean? So basically, the vis-a-vis symbol is a way of representing the cross product. So what we can do is, let's say I is 1, J is 2, and K is 3. So if these are symmetrized, so basically if it's 1, 2, 3, if we shift the indices to the left, so it will be 2, 3, 1, and we shift it one more, 3, 1, 2, this will always yield 1. But if we have some anti-symmetric combination, for example, if this is 1, if I is 1, J is 2, and K is 3, and we swap maybe 1 and 2, this will be 2, 1, 3, this will be a -1. Or if we swap 1 and if we swap 2 and 3, so we get 1, 3, 2, this will also be anti-symmetric, this will also be -1. And if these have repeated indices, this will be 0. So what does this represent? So remember that in the cross product, we always have some terms that are positive and some terms that are negative. So this encompasses the cross product, and by representing in this form, so basically this has 3 indices, right? And the partial j and partial k each have 1. So there's still an index remaining in the upper index. So this is essentially the curl, right? Because the curl of a vector always yields a vector. So this term without the eta term is the curl. The reason why I put this eta term here is because the eta is the Minkowski metric, and I wanted this I index to be the lower index. But if we just get rid of this and put this up here, this will just be b to the I, which is exactly the same, because these are Euclidean vectors, and dual vector is just the transpose, which is exactly the same, which has no bearing on the physical meaning or the mathematical meaning. So with this defined, we can write the Faraday tensor as follows, where Ex, Ey, and Ez are the x, y, z components of the electric field respectively, and Bx, By, and Bz are the x, y, z components of the magnetic field respectively. So the Faraday tensor can be written as follows, and notice there are 2 interesting properties of the Faraday tensor. One, it is antisymmetric, meaning if you swap these 2, you yield negative f beta alpha, and it's traceless, so any diagonal components are 0. So now we need to pick a convenient coordinate system. In other words, we need to pick a gauge. So let us pick a convenient gauge known as the Lorentz gauge. So basically, it is the divergence of the vector potential is equal to 0. And by doing so, we get this equation. And note that this equation is already quite similar to what we have, because we want to show. So basically, partial sub alpha and partial to the alpha yield is basically the D'Alembertian, and the D'Alembertian is essentially the wave operator. So we've shown that the wave operator of the Fourier potential is equal to some constant times the Fourier current. This is quite close to what we want, but it's not exactly what we want, because we want to show that the Fourier current. So sorry, we want to show that the wave operator acting on the electric field and the magnetic field is indeed a valid wave equation. So how do we do this? Basically, we can take the partial derivative with respect to gamma on both sides, and we get something like this. But we also have to add, well, not add, but subtract an antisymmetric part. And recall that this is the definition. So this term here, by subtracting the antisymmetric part, we yield the definition of the Faraday tensor. And then we get an additional term here, which is the antisymmetric part of the partial gamma j beta. So what does this mean? We have a generalized wave equation. So this is still a wave equation, right? But it's inhomogeneous, so basically has an extra term. But in this lecture, we are considering electromagnetic waves in free space. So basically, the charge density is 0 and the current density is 0. So therefore, J alpha is equal to 0. So then the equation reduces to a homogeneous wave equation. So basically, this is essentially the Lambertian, which is equal to 0. So this is a homogeneous wave equation. What is nice is, since f beta gamma, so for example here, right, has electric and magnetic field components, this infers that the electric and magnetic fields must also satisfy the wave equation. So specifically the inhomogeneous wave equation. So this is quite nice. We've shown that by showing that the Faraday tensor satisfies the inhomogeneous wave equation, this by virtue shows that the electric and magnetic fields satisfy the the homogeneous wave equation. So which is quite nice. So recall that in one dimension, we can solve the wave equation given some initial conditions, and we can use the Lambert solution. And also recall that a normal mode solution is a solution with one characteristic frequency. So in one dimension, the plane wave solution is as follows. So this is a wave propagating in the x direction. It's not technically one-dimensional because we have an additional vector here, but it's one-dimensional in the sense that it only has partial derivatives with respect to x. So this is the one-dimensional wave equation, where A is a positive real number that represents the amplitude, omega is a positive real number that represents the frequency, and k is equal to the frequency over the speed, the wave speed. So this is also a positive real number. And this is called the wave vector. So sorry, the wave number. So this should be the wave number. We'll show that it is a wave vector. We can use it as a wave vector later. And theta is the phase angle. And here, E bar is the polarization factor, which I will define later. But it's basically how the electric and magnetic fields, the direction for which they're pointing. So not only pointing, but directions for which they're oscillating. So in this case, let us, I guess I want to show the physical motivation behind why electric and magnetic fields, well, I want to show the shape of electric fields and magnetic fields in electromagnetic waves. So let the polarization vector be written as follows, where alpha, beta, and gamma are real numbers. Then, using Gauss's law, we can take divergence. Remember, Gauss's law has a rho term, but the rho term is zero because we're considering free space. So we get this equation, right? But note that f of x, comma t is y and z dependent. So this means that partial y of f and partial z of f are zero. Moreover, we get this equation, right? So we're left with this equation because these two terms are zero. But we're left with this equation. But partial x is obviously not zero. So this implies that alpha must be zero. So we can see that the polarization factor only has y and z components, namely beta and gamma. So given that the direction of propagation is in the x direction, the polarization vector is orthogonal to the direction of propagation. And to generalize this for plane waves, we can write the wave number as the wave vector, k to the I, and the position vector as x sub I, and the wave vector tells us the direction of propagation of the wave. And therefore, the plane wave solution can be written as follows. This should be an E bar, by the way. This is a mistake here. This should be E bar, not E sub I. So this is, and E naught is the electric field amplitude. So given some wave solution, basically, this should also be E bar, by the way. This is also a mistake, but it's not really that big. So basically, given some wave solution, we can always represent the, so basically, given the electric field, we can always find the magnetic field by taking the curl of the electric field, and then we take the time integral of both sides to yield the magnetic field. So the reason why this is also a cosine, right? Remember this electric field is a cosine, but when we take the derivative, we get a sine, and if we take the time integral, we get another cosine. So it's just this, and you'll find by solving this equation that the amplitude of the magnetic field is equal to the electric field over the wave speed. And generally, I think you've seen pictures of electromagnetic waves before. They look like this, right? And we have shown that, so basically the waves, the oscillations of the wave must be orthogonal to the propagation. So we can see that the propagation is in the x direction. So it's pointing towards the x direction. But these two must be orthogonal. So let's say the blue one is the electric field and the green one is the magnetic field, right? But I guess it is not quite obvious in this case why the electric field must be orthogonal to the magnetic field, right? Because we did show that the electric field must be orthogonal to the propagation direction, and the magnetic field must be orthogonal to the propagation direction. But we didn't show that the electric and magnetic fields must be orthogonal to each other. So it's not quite apparent in this form. So that's why I want to introduce a more beautiful form that will show this. So this is the complex representation form. So what is the complex representation? So once again, consider the wave equation as follows, where psi this time is the complex representation of the solution. Now, recall that Euler's formula is like this. And this is why I use E bar and E, because I don't want to get confused with the exponential and the polarization vector. So here we have the Euler's formula, and it works for any scalar variable x. So therefore, we can write the psi as follows. If we write psi as follows, we get this equation, because kj is a dual vector and xj is a vector, and the dual vector multiplied by the vector always yields a scalar function. So since these are not complex, complex vectors, this will always yield a real number. So this equation is still valid, right? So where we defined a tilde as equal to a times e to the I theta, which can always be a complex number, right? Because this need not, so unless this is like pi or any integer multiple of pi, this will always be a complex number. So given that a is a real number. So to obtain the real plane wave solution, we just simply take the real part of psi and we get this solution. So because the real part of this equation is just this, so it's quite simple. And there are advantages to using the complex representation. Not only is it more convenient, in my opinion, it is more physically meaningful. It is more convenient because it is easier to multiply and add exponential functions. It is more physically meaningful because we can see the relationship between differential operators and physical parameters. So let us write the electric and magnetic field in complex representation. So let us write it as follows. Now let us act the differential operators on the electric and magnetic fields. So here, let us take divergence. So if we take the divergence of the electric field, since we have x component here, right? We just multiply it by a factor of ik. So similarly, we do the same thing with the magnetic field. Here, we take the curl, right? So the curl, since we only have an xj component here, we take the curl of the, so we will find by doing this computation, we will get the curl of the electric field is the cross product of the wave vector and the electric field. Similarly, if we take the curl of the magnetic field, it is the cross product of the k vector and the magnetic field multiplied by I on this one. So here, if we take the time derivative, this yields, so basically if we take the time derivative of the electric field, this yields the negative I times the frequency. And if we take the time derivative of the magnetic field, we get negative I times the frequency of the magnetic field. So what does this imply? So we can see that the partial derivative with respect to the space variable yields I times the wave vector, and the partial derivative with respect to time yields minus I times omega. And this, I think, is quite beautiful because it's quite similar to quantum mechanics, where quantum mechanics and also classical mechanics, where spatial derivatives yields changes. So basically, in quantum mechanics, translations in space generates momentum operators, and translations in momentum yields space operators. And in quantum mechanics also, if we take time derivatives, that yields the energy operator. So here we see something quite similar. So the partial derivative with respect to space yields the wave vector, and the partial derivative with respect to time yields the frequency. And if we insert factors of h bar in here, I suspect we will yield quantum mechanics. See, because h bar times the frequency is the energy operator. So if we add factors of h bar here, we'll get the energy operator on this side. If we add factors of h bar here, so h bar, so remember the wave, what's this called? The wave vector is related to the momentum operator by some h bar factor. So if we multiply h bar here, we'll see that the spatial derivative generates momentum translations. So this has a nice correspondence with quantum and classical mechanics. So I also said that this makes it clearer that that the components, so basically the oscillations of the wave is orthogonal to the propagation. So I will show this right here, right? So we can see from Maxwell's equation that we can, from Maxwell's equation, we can see that the divergence of the electric field is always zero, divergence of the magnetic field is always zero in free space. So remember that the divergence yields, generates the wave vector in both cases, right? So this is essentially the dot product between the wave vector and the electric field and the wave vector and the magnetic field. So if the dot product between two vectors is zero, this implies that they are orthogonal. So we've shown here that K is orthogonal to E and K is orthogonal to B. But this still doesn't show that B is orthogonal to E. So from this, we need to use Faraday's law. So Faraday's law states that the curl of the electric field is equal to the negative time derivative of the magnetic field. So remember that the partial derivative always generates the wave vector, right? So here we have the wave vector, and the time derivative always generates the negative frequency of so it always generates negative frequencies. So we get this. So we can see that if we take the dot product of E on both sides, right? So if we multiply by E sub I, so we get this side will be equal to zero because we have a cross product with zero, a cross product with E, and if we dot it with E again, we should get something that is zero. And here we get Bi dot E sub I, which means that Ei dot E sub I is zero. So basically, if we dot the vectors, the electric and magnetic field vectors, if we take the inner product, basically, this will be zero. So this implies that the electric field must be orthogonal to the magnetic field. Now that we have discussed why the oscillation of the waves must be orthogonal to the propagation direction and why the electric and magnetic fields must be orthogonal to each other, now let us talk about the superposition of plane waves. So the linearity of the wave equation allows for the superposition of plane waves. In complex representation, it can be written as follows. So basically, the complex representation of the electric field can be written as some k-dependent amplitude and some oscillatory parts. And here is some k is a similar case, right? We have the k-dependent amplitude multiply some oscillatory parts is equal to the complex representation of the magnetic field. So what we can do is we can do a Fourier transform to get the following, right? So if we can replace these with integrals, right, if they're continuous. So what can we do? With initial conditions, we can use Fourier's trick to write the k-dependent amplitudes as the inverse Fourier transform. So what we can do here is let's set t to 0, right, and t to 0 here. So we have some initial conditions. So we get some, so basically the complex representation of the electric and magnetic fields at some initial time 0, t equals 0, we get this equation. So doing the integral, we get a function that is dependent only on k. So what happens is then we can simply add all possible E tilde naught and B tilde naught to obtain a superposed solution. So this is known as Fourier analysis. So we can just add these k-dependent amplitude terms to the complex representation of the electric and magnetic fields as shown here. So now that we've talked about the superposition of plane waves, we can talk about polarization. So polarization is a property by which transverse waves oscillate in a particular direction. So I guess for those of you who've done a little bit of optics before, in your undergraduate class, your professors have probably told you that linear polarization corresponds to orthogonal electric fields that are in phase. Circular polarization corresponds to orthogonal electric fields that are out of phase by pi/2. And the rationale, I don't know if they have ever mentioned the rationale behind this, but the rationale behind this I have already mentioned in my section on two-dimensional harmonic oscillators, where I've covered in my simple harmonic oscillators videos. But I will talk about them a little bit more here, and I will eventually talk about something more enlightening, namely the Jones vectors. So consider an electric field of an electromagnetic wave propagating in the z direction. So basically we only have, so since it's propagating in the z direction, the electric field can only oscillate in the x and y direction. So we have this where E naught of x and E naught of y and theta of x and theta of y are the amplitudes in the x and y direction, and the phases in the x or y direction, respectively. Now, let us define delta as the phase difference between theta sub x minus theta sub y. So it's the phase difference between these two. So using the compound angle formula, we get the following. So using the fact that sine squared x plus cos squared x is equal to 1, we can write the sine term as cosine term. And using this, we can write this entire electric field component, this y electric field component, in terms of the x electric field component. So let us do that. So we get this equation. So remember this, the subscripts with the 0 are just constants, whereas the ones without the zeros are the components of the electric fields. So if we rearrange the equation, we get this. And recall that this is an equation, well, this looks like an equation of a conic section because delta can be constant and these two will be constant. But it depends on what this constant is. So basically, let us consider some cases. So if the orthogonal electric fields are in phase, that means delta is some integer multiple of pi. So delta is equal to n pi, where n is an integer. So therefore, we get the conic section as follows, right? This still looks very ugly, but what we can do is we can always factorize. So we factorize this, and this is essentially a quadratic, but it only has one real root. One real distinct root. So this will be, so we square root both sides. This will be identical because plus or minus 0 is still 0. So what happens is we get EY is equal to plus or minus E naught Y over E naught X times times EX. So this is clearly a linear equation. That's why we call it linear polarization. So what does it look like? We can see in this figure, right? So let's say that the blue one is the electric field oscillating in the y direction, and the green one is the electric field oscillating in the x direction. So what we get is that since these two electric fields are in phase, they generate an electric field that is polarized. So basically, it only oscillates in one direction. So total electric field oscillates only in one direction. And it's not so apparent using this argument. I mean, sure, this is a linear equation, right? But it's still not so apparent why it should oscillate in one direction. I will explain this in more detail when I talk about the Jones vectors. But let us also talk about circularly polarized wave, or elliptically polarized wave, to be more general. So if orthogonal electric fields are out of phase by pi over 2, that means that means you have some odd number divided by 2 multiplied by pi, right? So this is some odd integer divided by 2 multiplied by pi. So we get the conic section equation that looks like this. And we can see that this is quite similar to an ellipse, but the right-hand side can also be negative, which is not the equation of an ellipse. But let's first consider the positive solution, right? So if this was positive 1, then this is obviously an equation for an ellipse. That's why we call it elliptically polarized. And if if E0x and E0y are equal, then this is the equation of a circle. So they'll be circularly polarized. But we have to keep in mind that delta is just the phase difference between the two. And we can always change the definition of the delta to, we can just swap the two variables, and we can get exactly the same phase difference. So we can define this in such a way that the right-hand side is also positive. But that is not to say that a negative sign delta is not physically significant. So let us examine the y component of the electric field again. So we get this equation, right? So let us make an inversion transformation. So from delta to minus delta. So looking at this equation, right? Since cosine is an even function, changing it from positive delta to minus delta makes no difference. But here, sine is an odd function. So changing it from a positive delta to a negative delta makes a difference. So a difference by exactly a sign. So now what happens is if we set delta to pi over 2, we get the EY component is minus plus E naught Y times sine times this sinusoidal function. So what does this mean? So looking at this total electric field, what do we see? This is the equation. So this is basically the parametric equation for a circle. But one of the components will always oscillate in, well, let's call it the positive direction, a positive x direction, right? But here, since we have a negative and positive solution, the other one can either oscillate in the positive y direction or the negative y direction. So this yields a not circular, but an elliptically polarized wave that is either moving, that's either spiraling clockwise or counterclockwise. So we have a special name for these, right? So yeah, as we can see here, we yield, as I mentioned before, we yield two different solutions, right? And the different sign gives us the handedness of the solution. So, and we can see this is more apparent when we look at a figure, right? So let us look at the electric field here. So we can see that the blue one, let's say, is the electric field in the y direction, and the green one is the electric field in the x direction. And in this case, E naught x and E naught y are equal, so we get a circularly polarized wave. But this doesn't really make a difference in terms of the physics, right? Here, we can see that they are exactly pi over 2 out of phase. So what happens is we generate a spiral that is going in the we can see the spiral going in this direction, right? So I guess if you use the right-hand rule like this, this is spiraling in the counterclockwise direction, right? So this is my right hand, so it's pointing like this. So this curl is curling in the counterclockwise direction. So what happens is we get a curve that's a spiral that's going counterclockwise. But this represents the positive solution. So this solution right here, where we have a positive sign in front of E naught y, sorry. And if we have a negative E naught y here, we get similar things. So basically, the electric fields are orthogonal and they are out of phase by 90 degrees, but it is spiraling in the counterclockwise direction. In the clockwise direction, you can see, right? This is clockwise. Yeah, you can see that it's going in the clockwise direction. So this is opposite to the right, or you can think of it, since it's negative, you can use the left-hand rule, right? So it's pointing, the wave is propagating in this direction, and the spiral is curling in the clockwise direction. So it's this way. So I guess why I want to talk about something additionally that I want to talk about is if you have arbitrary phase difference, something not so nice, let's say it's not pi, let's say it's like E or something, right? You may get something like the Lissajous curves, which I introduced in the 2D harmonic oscillators. So yeah, you can get similar curves by this. But I want to talk about something more enlightening, and this concept, I guess, was inspired by a video that I watched some time ago by Chris, where he showed that the Jones vectors are so basically the Jones vectors are essentially spinors, and he showed the connection between these two properties, and I think it's quite mathematically nice. And he did explain why the Jones vectors generates the shape that they do. But I want to talk about some other more complex shapes that you can use, that you can generate using the Jones vectors. Because the point of his video was just mainly to show how the Jones vectors are related to spinors. It's not really, it's more, I would say, more mathematical than physical. In this case, I want to show the geometric picture a little bit more. So this is the novelty, I guess, of my video. So there's another way to represent polarizations using Jones vectors, which leverages the uses of complex representation. So the electric field in complex representation can be written as follows. So basically, I just replace the cosine functions with e to the I, blah, blah, blah. So basically, I will define E tilde as so basically E times the some exponential function times I times the phase, right? So we can define it in this manner. So if we define it like this, we get this vector, right? So we get E tilde naught x plus E tilde naught y times the oscillatory part. So since the oscillatory part is the same, it doesn't really well, it doesn't really yield much information about the direction of propagation. So what we can do is represent this part, so the E naught x part, as a new vector called the Jones vector. And for those who do quantum mechanics and quantum information, we can write this in Dirac notation. So whereas where ket of 0 is the x unit vector, and ket of 1 is the y unit vector. So this can be written in Dirac notation quite nicely. So the Jones vector can be written like this. So there are many reasons why I personally like the Jones vector. So because it more clearly tells us the direction of polarization. So that E naught x and E naught y be real in this case, right? So we want to talk about linearly polarized waves. So if these two are real, then this immediately tells us that the wave is linearly polarized. With regards to the direction, let us consider the Jones vector as follows, right? So for convenience, let us normalize the vector. So when we normalize it, we just divide by the magnitude of two vectors. So the sum of the square of the two vectors, and then we divide by that. So how we get the magnitude, we square these two, sum them, square root it, and then take 1 over that square root. So that's the so that makes this vector essentially normalized, and it's a unit vector. So clearly the magnitude of the vector is alpha squared plus beta squared, and the direction of the vector is this, right? So let us consider a simple case. Let us say that alpha is 1 and beta is 1. So what does that mean? So if these two are 1, then we get 1 and 1, and we get 1 over the square root of 2, right? So so if alpha is 1 and beta is 1, that means we have the magnitude of the vector. So we have square root of alpha squared plus beta squared, and it's pointing in the direction. So it's pointing in a particular direction with this magnitude. But since we divide by this factor, we always normalize the magnitude to 1, so it's pointing some direction. But let's say, so since we said alpha and beta are both 1, so we get 1 over the square root of 2. What is our cos of 1 over the square root of 2? So this is simply 45 degrees, right? So it is quite simple. So it's basically, if we have an addition of this vector and addition of this vector, we get another vector pointing this way by vector addition. So we can see that using the Jones vectors, we can get the direction of a linearly polarized wave simply using vector addition. So the Jones vectors tells us a lot of information. But now, in the previous case, we always talked about real real numbers, real vectors. But what if we have complex vectors? So before we move to complex vectors, let us consider a case where the x component is real and the y component is imaginary. So this will tell us that the vector is this Jones vector will tell us that the wave is elliptically polarized. And how does this tell us? So we can do the same thing. We can get the Jones vectors, but we normalize it as well. Excuse me. And the way that we normalize it with complex numbers is instead of just taking the square, because if you take the square of this, you get negative beta squared. And if beta is greater than alpha, right? So let's say beta is greater than alpha, then you get an imaginary length, which is not physical. So what we do is we multiply by the complex conjugate. So it's the same as taking inner products in quantum mechanics. So let alpha and beta be real. So let us take the real and imaginary parts, right? So we can see that if we take the real and imaginary parts, we can see that we have one part of the wave here is oscillating on the real axis, and the other one is oscillating in the imaginary axis, right? And this yields a ellipse. But what is the shape of this ellipse, right? So let's assume that beta is greater than alpha, let's say. This yields an ellipse with a semi-major axis of this. So basically this term, the imaginary term, represents the semi-major axis. And the real term represents semi-minor axis. And if we flip this inequality around, right, this is alpha and this is beta, they basically switch. So one is the semi-major axis and one is the semi-minor axis. So we just swap the two axes. So this is the motivation as why I like to use Jones vectors, because it tells us a lot of information about the polarization of the wave. Now let us consider a little bit on another more complicated case where the x component is real. but the y component is complex. Then the normalized Jones vector is as follows. We get this equation, and what we do is we have, so basically it's exactly the same as what I did just now. We normalize it and etc. But in this case, let us see that what happens when we decompose A. Let's decompose A into alpha 1 and alpha 2. So we can separate the vector like this, right? Notice that since the wave equation is linear, we can always superpose waves. So this part, remember, is similar. Remember, it's actually not only similar, it's exactly the same to that of this one, right? It is just the Jones vector for a linearly polarized wave. This part here is the Jones vector for an elliptical wave. So elliptically polarized wave, right? So if we add these two together, it is simply an ellipse where the semi-major axis is oriented in the direction where the linearly polarized vector is pointing. So it's basically an ellipse where the semi-major axis is oriented in the direction where the linearly polarized vector is oscillating. And if we get both of them are complex, we can just do the same trick, right? We can just add, four different waves, right? We can add one with a linear component, another with a linear component, and one with a circular component, and one with a circular component. So this is very similar, but you may get very, very complicated curves because you may even get Lissajous curves because they are I guess you can represent it as, I guess these are arbitrary complex numbers, and so you will get very complicated curves. And I realized that this is quite beautiful because I have a friend that I met in my in one of my scholarship events, and his name is Simba, and he's also a graduate student preparing to do his PhD in U Toronto, and he does research on quantum information and quantum computation. And he actually taught me the concept of Bloch spheres, which I never knew. And he taught me how any arbitrary ket vector can be represented on a Bloch sphere. So I realized that this is very similar to the, actually any Jones vector can be represented, any solution to the Jones vector can be represented on a Bloch sphere, because let's look at one of the equation, right? Let's say that the Jones vector looks like this, right? If we normalize it to look like this, we get so basically the magnitude will always be a unit vector, but it would just be vectors pointing in a different direction, right? So let us say alpha and beta are not only real numbers, let us make them complex numbers. So basically all solutions to the not all solutions, but every single Jones vectors, like in quantum mechanics, can be represented on the surface of a Bloch sphere. So in the case of linear polarized wave, it can be some wave, so it can be some vector pointing in this direction. Some circular polarizer is another vector pointing in another direction. So yeah, so the pole here represents the zero ket, and the antipole represents the one ket. So this solution is any solution to any Jones vectors can be represented as a point on the Bloch sphere. So this is quite a beautiful argument, and it has a nice correspondence. I guess what is nice about this is that a lot of the phenomena in optics have a nice correspondence to that in classical mechanics and quantum mechanics. So notice that here we have not introduced any quantum mechanics, right? This is a purely classical argument, yet it has a beautiful correspondence to a concept in quantum mechanics, namely the Bloch sphere. Similarly, in the electromagnetic, when we did the complex representation, right? We see that there is a very nice correspondence between derivatives and physical parameters, which is exactly the same as that in quantum mechanics. So I think the beauty of learning about this, researching about this lecture, is that I found that there was a nice correspondence between classical optics and quantum mechanics. So I found that quite nice, and I hope that you've learned something from this lecture. And if you're interested in optics, I'll talk more about it in the next lecture, which I think in the next lecture I'll talk about refraction, and diffraction. So I will talk about the boundary conditions of the Maxwell equations. So I'll see you next time. Thank you.